The normal force is a sneaky force. We don't have an equation that easily gives us its size, so we always have to figure it out from the situation, depending on the other forces and what's happening. So let's take a look at how the normal force changes depending on the situation. Here we have a student who is lowering a textbook that is sitting on their hand. For the interaction diagram for this situation, we have the book as the system. The book is interacting with two objects, the hand and earth. Now let's remember, when we label an applied interaction, we understand that is a normal interaction between the hand and the book. Now we have three different intervals that all use the same interaction diagram. There's no new interactions going from one interval to the next. All that's changing is the strength of the interaction. So let's take a look at how that appears in our force diagrams. In interval 1, 2, we're told that the binder is moving downwards and it's speeding up as we've lifted it off and are beginning to lower it. So if it's speeding up, the state of motion is acceleration, and the state of force is going to be unbalanced. Because it's unbalanced, our two force vectors can't be equal in size. It's moving downwards and speeding up, so this tells us the acceleration has to be in the downwards direction. So we're going to have two vertical forces, a gravitational force and an applied force, and the downwards force needs to be the larger one. So let's show that here. Here's my force of gravity downwards, and this needs to be larger than the upwards applied force. So using our knowledge of the motion, we've figured out what the size of the applied force is like. Let's take a look at the next interval. The book is now moving with a constant velocity, and so we want to draw the new force diagram. So, state of motion, constant velocity. That means the state of force is balanced. So if we think about what changes going from one force diagram to the other, the mass of the object did not change. And so we want to do our best here to show that these two force of gravity vectors are the same size. So that is the same size as that. But now that it's moving with a constant velocity, the applied force has to be different. The applied force, since the forces are balanced, must be equal in size to the force of gravity. In the final interval, the book is slowing down as it reaches your desk. So that means the state of motion is acceleration and the forces are unbalanced. Since it's slowing down, the acceleration must be pointing upwards. So it's moving downwards and it's slowing down, so the velocity has to be the opposite direction. So we know that the acceleration in this situation must point upwards. The force of gravity has not changed size, so we're going to be really careful about that. So all these three force of gravity vectors are the same. But now, because the acceleration is pointing upwards, we know that the upwards applied force must be larger than the downwards force of gravity. So here we see the normal force is changing in size depending on the situation. We could set up our expression for the net force in the y direction to solve for the size of it in this situation here, where the forces are balanced. In these situations here, we need some more physics skills in order to figure out the size of the applied force while the object is accelerating. That's coming up very soon.